Okay, so let me write out again the theorem to verify that the full branch map has bounded distortion, right? So this is the theorem we're going to check today. There's two kinds of chalk. So, if F is a full branch map, C2 full branch map, suppose F suppose that F is uniformly expanding. And we suppose too that the supremum over all omega in P and the supremum over all xy in omega of the second derivative. I think I've been using two slightly different notation. Let me just use for consistency this notation. Fx dfy squared less than equal to k. So uniformly bounded. Okay, then there exists some k tilde greater than 0 such that for all n greater than equal to 1, for all omega n in Pn, this is the refinement, okay, for all xy in omega n, we have that the log of dfn of x over dfn of y is less than equal to k tilde fn of x minus fn of y, which is therefore less than equal to k tilde, which is uniformly bounded. Okay, this is a slightly technical statement, but if you remember, this is the distortion. So the maximum over all xy, the supremum over all xy of this is the distortion. The fact that this is uniformly bounded for all xy, for all n, for all omega n, and for all xy means that this map has uniformly bounded distortion. So in particular, F has bounded distortion, or uniformly. I can't remember what uniformly bounded distortion. And the reason why we need this kind of theorem is because the bounded distortion is a property that is a property that is stated for every n. Okay, whereas the conditions here are in principle verifiable even just for one iterate of the map, right? So the difference between the assumptions and the conclusion is that the assumptions just look at the map. For example, if the absolute value of the derivative is bigger than 1 everywhere, then F is uniformly expanding, and this is something that involves the second and first derivative, but it's just for the one iterate of the map. And we use this to show that the Gauss map satisfies this property, right? And therefore the Gauss map has bounded distortion. And then what we did, we proved that in this case also, what is our conclusion? Because we had a theorem that if a map F is full branch and has bounded distortion, then Lebesgue measure is ergodic. Okay? So Lebesgue measure is ergodic. In fact, so uniformly bounded distortion implies Lebesgue measure is ergodic, and this in particular implies that if we have any other measure that is absolutely continuous, right, for any mu that is absolutely continuous with respect to Lebesgue, then mu is also ergodic. Right? Remember there was a little lemma that showed that if two measures, one's absolutely continuous with respect to the other, and one is ergodic, then the other one is ergodic. So we use this to show that for the Gauss map, we had a measure that is invariant and absolutely continuous with respect to Lebesgue. So we use this chain of implication to show that measure is ergodic. Okay? This was the structure of what we have done so far. So what we're going to do today is two things. First of all, we're going to prove this. This is fairly straightforward, okay? And then we're going to do, in some sense, what is the main theorem. We're going to start what is, in some sense, the main theorem of the second part of the course, which is to show that any map satisfying this actually has an invariant measure that is absolutely continuous with respect to the bank. Okay? Because what this theorem, what this chain of results says now is that if you have these properties, then you have bounded distortion, so Lebesgue is ergodic, and if you have a measure that is invariant, I don't need to put invariant here logically, but what we're interested in is the case in which mu is invariant. Okay, if we can find a measure that is invariant and absolutely continuous, then it is automatically ergodic, and we're going to show that in fact under these conditions you always have a measure that is invariant and absolutely continuous with respect to the bank. Okay, which is a generalization of what we have for the Gauss map. In the Gauss map we have an explicit version of this measure. We're going to show that very generally. So that having, and in particular, therefore, it's a physical measure. If you remember, we proved that any measure that satisfies this is also a physical measure because it has a basin that has positive Lebesgue measure. Okay, so the first thing we do is let's prove this theorem here. So the first lemma prove this theorem is we suppose, okay, under these assumptions, we have that for all, so under the assumptions of the theorem, under assumptions, in fact, sorry, we don't need both assumptions, just under assumption 2, so under 2, or in theorem, we have the following, is that for all omega in P and for all xy in omega, we have the df of x over df of y minus 1 is less than or equal to k f of x minus f of y. So this property here is just a kind of, so you can see of course that when f of x equals f of y, then x equals y, right? And then these two derivatives are the same. This is 1, so this is 0. Okay? This is saying that when x is different from y, this ratio is different from 1 by something that is kind of Lipschitz in some sense in terms of the images. So it's a slightly technical property, but we will see how it is used. It is kind of telling you how this is varying. And I will just give you, this is a very simple exercise, so I will essentially leave it as an exercise, but let me give you a hint here that is very easy exercise. But let me give a hint, is to use the mean value theorem twice, okay, both for the, so we have 2 points omega, so we have omega, and we have f, and we have f of omega, right? And here we have the points x and y. Okay. So what does the mean value theorem says? The mean value theorem is there exists psi1 in here and xy such that, so this is f of x and this is f of y. Right? So it tells you that there is a mean derivative here, right? So it says that f of x minus f of y is equal to the derivative df in psi1 times x minus y. Okay, you recognize this is the mean value thing, but we can also use the mean value thing for the derivative. So there also exists psi 2 in xy such that dfx minus dfy is equal to the second derivative of f in psi 2 times x minus y. Because the derivative is also a function. So, and it varies continuously, and the second derivative says how it varies. And so if you look at the derivative here and the derivative here, the derivative of f in x and the derivative of f in y, it satisfies this property. Okay, and then you just put these two together and you easily get it. We'll leave it to complete as an exercise. Okay, this is very easy. You just divide through. Here you've got fx and x minus y, and you easily get this.
F of x.
That's when you get this. Sorry?
The last is f of x minus f of y, or just x minus y?
No, this is
Okay.
this is just x minus y because it's the distance between the 2 points. Okay, so this is a fairly simple lemma. Now we're going to do the main calculation involved in this proof, which I think is actually a very interesting calculation. So there's 3 lemmas for the proof of this theorem. And the next lemma is the following. It says that lemma, so f C2 full branch satisfying, so let me call this 3 actually, okay, satisfying 3. So we had 1 was the uniform expansivity, 2 was the ratio between the first and second derivatives that I put here, and 3 is this. So this lemma actually only needs this, but this, in fact, we could have stated the original theorem with this assumption here, but this is not as intuitive or not as checkable as assumption 2. Right? So satisfying 3, then for all n and for all omega n in Pn, we have the distortion of Fn on omega n is less than or equal to k times the sum I equals 1 to n of Fi omega n. So we're going to write out this, the calculation that gives this, and then we're going to try to get a uniform bound on this, right? Because what we're trying to show, what the statement says, is that you have uniformly bounded distortion, so that this is bounded by something independent of n of the interval. Right? So let me write down the calculation. For this is very simple. This is just really one line. So the distortion so what we need to bound is, remember that the distortion dfn of omega n is equal to the supremum of all xy in omega n of log of dfnx dfny, right? So this is the distortion. So we need to bound this term here, okay? So we write log of dfnx over dfny is equal to log, and now we just use the chain rule for dfn of x, right? So remember, this is just the product of the derivative along. So this is just the product of df in fi of x, I equals 0 to n minus 1, and this is just the product, I equals 0 to n minus 1 of df fi of y. Okay, and I can just write this as a uniform product, so this is just log of the product, I equals 0 n minus 1 of df fi x over df fi y. So stop me at any moment if there's any problems, right? And this is equal to the sum of the logs, the sum of the logs of df in fi x over df in fi y. And this I'm going to write as equal to the sum. I'm going to add and subtract. This is equal to the sum of the log of df fi x over df fi y minus df fi y over df fi y plus df fi y over fi x fi y. Okay, now I've just done a kind of trivial step of adding and subtracting 1, right? There's nothing there, but the reason is because I want to combine these two, and I'm going to get something that looks a bit like this. So this is equal to the sum of the logs of, here I combine this with this numerator, so this is df in fi y, and here I get df in fi x minus df in fi y plus 1. Okay, and now I'm going to get rid of this absolute value, and therefore I need to write this less than or equal to the sum of the logs, and now I'm going to make it the absolute value of the sum, so I write this as the absolute value of df fi of x minus df of fi of y over df fi of y plus 1. And this I can now write, so this is the absolute value I've put here now. Okay, I've turned this into an inequality, and this I can now write as less than or equal to the sum of just the log of this. Log of df fi of x minus df in fi of y over df of fi of y. So why is this? This is just general property that log of 1 plus x is less than x. Right? So if you take the log of 1 plus x, so when x is equal to 0, this is the log of 1, so it goes something like this, I think, right? And this is x, so it's just that log of 1 plus x is less than x. Okay, it's just a general term. So I can lose a little bit of this, but that's fine, because in general this will be very close, will be very small. And now I go back. So I've done all this palaver just actually to now resplit this again as I had them before. So this I can write actually as, this should be, sorry, the whole purpose was to get rid of the log here, sorry. Right, so this is log of 1 plus something, okay, positive, is less than something, which is this x, right, for x positive. In fact, always true. Okay, so I got rid of the log, so I got them here, and this I can write as equal to the sum, this is always from 0 to n minus 1, of df in fi of x over df in fi of y minus 1. Okay, so gone. I've just taken a very long detour to go from this basically to this. Maybe there was a more immediate way to see it. But now we applied, remember 3. Okay, we had the assumption 3, which is exactly with something of this form. And what this was saying 3 is that this is less than equal, each of these is less than equal to sum I equals 0 to n minus 1 of k fix minus fiy, right? Minus fiy. Okay? And because x and y are belonging, so we've chosen x and y for xy in omega n, okay, then this is less than or equal to sum I equals 0 to n minus 1 of fi omega n, which means I think maybe I got the indexing wrong here. Why do I have from R1 to N? Why do I have from 1 to N? Because this is Fi, so because this is not I equals 0, right? So, yeah, right, so when I go from here to here, I'm saying that for I equals 0, I have x and y here, and I bound it by f of x minus fy, so this is actually from 1 to n, right here. Because when I go from here to here, if you remember the form of 3, for I equals 0, I have x and y, and so I get that the term I equals 0 is bounded by f is bounded by the case I equals 1 here, right? So I need to add one index here, so you can check. And so this is actually I equals 1 to n. Yes. Okay, so I encourage you to make sure that you learn this calculation. However simple it is a kind of quite crucial calculation because it gives the distortion in terms of these sizes of the images of this image. Okay? Now, this allows us to then, the problem now, to consider the problem of how to bound this. Okay, and this is very curious because what we're wanting is some bound, so to complete the proof of the theorem, to show that it has bounded distortion, exactly what we need to say is that this bound is uniformly bounded independently of n and independently of omega. Right? That's exactly what we want to show. Now this initially seems contradictory, because what happens if you take n large? What happens if you take very large n? Then we have a very long sum. We have a very large sum. So how can this be uniformly bounded in n? If you take very large n, you are adding more iterants, right? And more or less, what's happening to the images of omega n? Is this sequence increasing or decreasing the size of fi of omega n? It's increasing because the map is expanding. So how can we hope we have this increasing sequence? If we take n large, it's increasing even more. How can we ever hope to get a uniform bound independent of n? So this is the picture we have our omega n, right? And then we have here some intermediate fi of omega n, and then we have at the end we have fn of omega n, right? And we want to sum all the lengths. And that's the bound for the distortion, right? So the distortion is the comparing the derivatives. Here we have 2 points x and y. So for any 2 points x and y, this is the maximum distortion over all points x and y omega n. So we found a bound for any 2 points x and y. The ratio of the derivatives is bounded by this, which is the sum of the sizes of this. Okay? So how can we hope for this sum to be uniformly bounded? I think. Any ideas? Monica. Because a priori you say, okay, we've got a bound which is very clever of us, but we really did a calculation that gave us a boundary which is no good, because if you take larger n, maybe this is getting bigger and bigger and it's unbounded and it's no good.
We said that the k doesn't depend on n.
Excuse me?
We said that the k is independent of n.
The k is independent of n because the k is the original k that you find in phi. It's just fixed once and for all. Right? This k here comes from just the assumption that we satisfy phi, and then we show that for every n, for every omega n, we have this property here. Okay? So it's really all in the sum.
It's increasing.
I don't know. This is what we would prefer not to know. Remember that intuitively this kind of makes sense, right? Because if you remember when we gave that kind of little heuristic discussion about the distortion, we saw the distortion is the ratio in the intervals, right? You take all of the derivatives along the interval, you take 2 points. The bigger the intervals are, and the bigger you might have a variation of the derivative between 2 points, right? So it's kind of makes sense that the size of the interval comes into it, right? So this kind of bound is intuitively makes sense, but doesn't give us something that is.
But it's kind of tricky because the omega n are becoming smaller.
Sorry?
Because the omega n are smaller.
The omega n are small.
Are smaller. As it goes.
Yes.
As it increases. So it's tricky.
So what?
It's tricky to decide up to now.
It's strictly what?
It's tricky up to now decide how much this increases.
Sorry,
Because
say
the
that
same-
again.
I mean, this series is not so immediate because, as I said, this omega n decreased.
Yes.
So despite we are adding more terms, it
Yes.
can become also smaller.
Yes. Correct. Okay, this is the key observation. So the key observation is that there is a hidden dependence on n, in the fact that omega n depends on n. Okay, so it's true that we want a uniform bound independent of n, but notice that these objects are not independent of n, so this is independent of n. So actually, how big is at time n, how big is Fn of omega n? What is Fn of omega n? Is equal to the interval. Always. Whatever. This is equal to the interval. Right? And what do you know about the previous steps? They're smaller. In fact, we're going to give a bound on how smaller they are. Okay? And as you said correctly, when n is big, it must mean that you're starting with a very small interval. Okay? So when you're summing here, it's true that you're summing a larger and larger number of intervals, but you're summing starting from an interval which is much smaller. Okay? So this is exactly going to be the key to this. Okay? This is exactly why we will end up getting a bound that is independent of n, because there's an implicit hidden dependence here. Okay? Because now this, what have we used so far? We've used 3 to get this, right? But now we have not used the uniform expansivity yet. Okay? So what does the uniform expansivity say? The uniform expansivity allows us to give bound for the size of the preimage in terms of this. Right? Again, by the mean value theorem. Okay? So remember, by the mean value, so wait, let me state this as the lemma we want to prove. So the lemma we want to prove is that this lemma is that if f full branch uniformly expanded, then there exists k tilde greater than 0 depending on C lambda. Remember C lambda are the constants that define the uniform expansivity. Okay? Such that for n greater than or equal to 1, for all omega n in Pn, and for all xy in omega n, we have that the sum I equals 1 to n of fi x minus fi y is less than or equal to k tilde fn x minus fn y, which is just less than or equal to k tilde, right? Because if this is less than or equal to 1, if you're in a unit interval, then this is less than or equal to 1. So this sum, okay, which is basically this sum here, so for any 2 points, if you take x and y to be the endpoints, then this is exactly the sum here, is less than or equal to k tilde. Uniform bound independent of n. Okay. And how do we use the uniform expansion? Well, it's easy. We look at some point here. Okay, so this point here, we look at what is this map here. This map is f n minus I from here to here. Right? From here to here, this is fn. From here to here, it's fn minus I. And now we know by the mean value theorem that there exists some point here, right? So we have some, what do we call it? Let's call it psi n minus I. So by the mean value theorem, proof, by the mean value theorem, we have that fn x minus fn y is equal to f is equal to the derivative df n minus I in some point psi n minus I times fi x minus fi y. For some, there exists some psi n minus I in this interval fi of x, fi of y. Right? So here we have x and y. Here we have fi of x. Here we have fi of y. So here we have this interval here. Okay, and here we have fn of x and fn of y. Okay, so by the mean value theorem, when we look from here, we look at fn minus I maps fi omega n to fn omega n. Okay, and by the mean value theorem, we have this property here. We have this, and what do we know about the derivative? Remember, what is the uniform expansivity property? It says that this is greater than or equal c e to the lambda n minus I times fi x minus fi. Yeah, this is the uniform expansivity that says that the derivative at every point of the iterates is greater than c e to the lambda times the number of iterates. This is going like this. Okay? And this allows us, what we want is actually a lower bound on this, because what we're going to show is that this is a geometrically converging sequence backwards. Okay? This is the key point. So we paradoxically, when you first look at it like this or like this, you see that this is, and using the uniform expansivity, you see that this is geometrically increasing, right? So you see that actually these intervals are increasing exponentially fast. But using the key fact is that you have a uniform bound for the last iterate, then what you actually use this fact to turn it back on its head and show that backward it's geometrically decreasing, right? So what we have here is that fi of x minus fi of y is less than or equal to c minus 1 e to the minus lambda n minus I times fn of x minus fn of y. So what we're seeing is that these intervals are geometrically decreasing in terms of the last one. Okay, and then we just sum up, which is what we're looking for, is the sum. So we take the sum, I equals 1 to n of fi x minus fi of y is less than or equal to, so we just take the sum. So this is just c minus 1 times the sum of e to the minus lambda n minus I times fn of x minus fn of y. So this is I equals 1 to n. Okay, so I've just plugged in. This is for each individual intermediate iterate. I have this condition that tells me that this is exponentially small in n minus I. Okay? Now notice that when I equals 1, this is n, so let me just make one more step here. This is equal to c to the minus 1, the sum. Now here I can write it as, I want to write it as e to the minus lambda I. Okay? So when I can write it like this, because when I is equal to 1, this is n minus 1, and when I is equal to n, this is 0, right? So this is just I equals 0 to n minus 1. Okay? This is the same sum times fn x minus fn y. Okay, and this is obviously Everything okay here with this transition here? And this is now obviously less than equal to the infinite sum, right? So this is c minus 1 times the sum I equals 0 to infinity of e to the minus lambda I. So this is going to be the new constant times fn of x minus fn of y. Okay, and this is a constant that is now independent of n. So this is exactly k tilde. Okay, so this completes the proof of the theorem that I wrote at the beginning. I really encourage you to make sure you go through this whole proof. It's a kind of little, maybe the most technical step that we've done in the course, but it's very simple calculation, and it's somehow this, as we showed from the beginning, this control on the distortion turns out to be the crucial ingredient in a lot of things, right? The control on the distortion gives the ergodicity of the Lebesgue measure, right? And therefore the ergodicity of any measure is absolutely continuous. So this happens also in higher dimensions. In many situations, distortion seems to be the main technical problem in understanding the ergodic properties of a system. And this is a kind of fairly fundamental, it's in a simple setting, but it's a fairly fundamental argument to control the distortion based on certain properties of the original map. Okay, so this is a useful technical point to start. So let's just take a couple of minutes break now, and then we'll go. Good. Okay, very good. So now we have finally reached an important point here, where we now want to construct invariant measures. So just to give an idea, so if you have a full branch map with a finite number of branches, where the derivative is bounded above and below, and the second derivative also, suppose you have some kind of full branch map, f I to I, C2, full branch. Okay, then what are the two conditions we just said we need? We need that uniformly expanding, okay, and then we need that conditions that said that the supremum of the second derivative, not consistent, the second derivative of x over the first derivative squared is bounded. Okay, the second derivative over the first derivative. So in the Gauss map, both the first and second derivatives are unbounded, and so to show that this ratio is bounded is, well, it's still fairly simple, but it's not completely trivial. But if you have a map with a finite number of branches, if the first and second derivative are bounded, uniformly bounded everywhere, which is a very natural, not a very distinctive condition, then you automatically have this property, right? If the first and second derivative are uniformly bounded above and below. But in fact, you just need the first derivative to be bounded below, the second derivative to be bounded above. Okay, so then what I'm trying to emphasize here is that these are very general conditions, very easy conditions to satisfy, okay, for a full branch map. the derivative bigger than 1 everywhere, so not really like this, bigger than 1. Okay, so under these conditions we have proved that Lebesgue measure is ergodic. Okay, so if we find any measure that's absolutely continuous and with respect to Lebesgue and invariant, then we will show it's ergodic, and then we'll show that this implies it's a physical measure, so we have all our kind of ergodic description of this system. Okay, so what we're going to prove today is that what we're going to start the proof at least is the following theorem. Okay, do you have a question on it? Okay, okay. Theorem, suppose F is a C2 full branch map satisfying these two, satisfying 1 plus 2. Okay, then there exists a unique ergodic invariant probability measure mu, which is absolutely continuous with respect to Lebesgue. So we have seen so far two special examples of this, right? We have seen the piecewise affine case. So the piecewise affine case trivially satisfies both of these conditions. And in that case, Lebesgue measure is itself ergodic and invariant, is the unique ergodic and invariant probability measure, which is absolutely continuous with respect to itself. And we've seen the Gauss map. Right? So the Gauss map, in which we verify these two conditions, is non-complete trivial, and it also satisfies this. In both cases, we have an explicit invariant measure. In general, we will not get an explicit formula, but we'll show there exists one. Right? It's really not obvious, this existence, because remember, invariant measures says you take an interval here, right? And then you look at the pre-images, you look at the sum. So this is going to have the pre-image is going to consist of a certain number of components, one inside each branch. And what the invariance of the measure says is that if you measure each of these, the sum of these will give you exactly this. Okay? If it's piecewise affine, then this is just the length. If it's not, then of course it depends, because if you take an interval A here or an interval B here, then because of the shape of the graph, you will get different lengths here, and so the measure has to somehow magically keep track of exactly the weighting. The measure gives some weight on the intervals, which guarantees exactly that for any interval, the sum of the pre-images gives exactly that. Okay, so it's kind of difficult to see that you can actually, calculate, which in general you cannot. Okay, we will give an abstract argument that shows there exists one, but that is the spirit of that. Okay, we will show a little bit more structure of this measure. So if you remember, whenever a measure is absolutely continuous, you have the Radon-Nikodym derivative of this measure with respect to the Lebesgue, right? So it's the density. So we have a little bit more information, and so moreover, d mu by dm by d Lebesgue is Lipschitz continuous. Is Lipschitz and bounded above and below, and bounded above and below. So this is just some additional information about this, which can be useful in several cases and several applications. Okay, so we are going to, in some sense, construct, in some way, construct this measure. And we need to use the dynamics because the invariance, to get a measure that's invariant, you somehow need to use the dynamics to construct it. And so the first step is to define a sequence of measures, mu n, to be equal to exactly the push forwards of Lebesgue measure. So 1 over n, the sum of f star Lebesgue measure. Did I use, is it okay if I use m for Lebesgue measure? I'm just used to using that. Okay, so I'll just use m. M is equal to Lebesgue. So I equals 0 to n minus 1. Have you seen this before? We've seen this kind of averages before, remember? When we proved the existence of invariant measures for continuous maps. Remember when we proved the Krylov-Bogolyubov theorem, and we just took any measure here, and we take the average of the push forwards, and we show that any accumulation point, so this is a sequence of probability measures. Remember, we use the fact that if you're in a compact space as we are, then the sequence of probability measures is compact. So this must have some accumulation points, and we already show that every accumulation point is an invariant measure. Okay, we won't actually use this here. We will show directly. We will. Our strategy will be to consider some accumulation points of this and show that it is invariant and absolutely continuous with respect to Lebesgue. Okay, we will do it directly, but I just wanted to remind you that we've already shown that in certain situations this is always invariant. Because we're using the dynamics, okay? If you remember that argument, it's worth going back to it. We get the invariance because it's intrinsic in this that we're using the dynamics, so we are moving, because the invariance of the measure, remember that mu is invariant if it is a fixed point of this, right? So if f star mu is equal to mu, right? So in some sense, the accumulation point turns out to be a fixed point of this operator. Okay, this is what is behind it. But this is just a little aside. Okay? So the problem now, the main problem will be to show the absolute continuity of these accumulation points. So first of all, notice that mu n is absolutely continuous. Right? Notice that mu n is absolutely continuous with respect to n. You agree with this? Because remember, what is the definition of f star n of A is equal to n or fi, f minus I of A. Okay? So if A has 0 Lebesgue measure, f minus 1, f minus I of A has also 0 Lebesgue measure, because the map is expanding, so it's non-singular. And so the measure is 0, and so this is 0. So if you take, okay, so if the measure of A is equal to 0, this implies that mu n of A is also equal to 0. Okay, so we have a sequence of measures that is absolutely continuous with respect to Lebesgue. Now, does that automatically imply that an accumulation point is also absolutely continuous? If we could do that, we resolve more or less. So let's do a specific example. Let's try to do this construction. Let me actually get a bit more space here because this example is very instructive. And I'm going to show that this is, the limit is not necessarily the case. So I'm going to do the example not for full branch expanding maps, because in that case we want to show that it is. And let's consider this example that we've done before, which is simple, just f of x equals 1/2 of x. Right, so remember, so we have here 0, 1. This is 1/2. So this is the graph of f equals 1/2 of x. Okay, so let's look at these measures. So what does f star look like? So we have f star of n. Wait, let me write it here. So what does f star of n look like? This is a measure, f star of m. Okay, f star of m is by definition measure of f minus 1 of a. So what is the measure? If I take a set A in here, well, I'm taking, okay, again, let's always remember that we are, okay, the measure lives on the interval 0, 1. Let's not confuse the graph, the map. Okay, so the measure is in 0, 1. Okay, this is 1/2. Okay, let me take a set A here. And I want to know what is the measure f star n of A. Okay? And I use the graph to help me understand that. Yes? Right. Okay? Because the measure of f minus 1 of A, if A is here, then you look at f minus 1 of A. This is f minus 1 of A. Okay? And you look at the Lebesgue measure of this, m of f minus 1 of A, is equal to twice the Lebesgue measure of A. What about if I take my set A here? Zero measure, because it does not have a pre-image. Yeah? So what does the density of this measure look like? What is the density d mu d f star n by dn? What does this look like? So remember, the density is the Radon-Nikodym derivative, so it has the property that it's defined by the fact that mu of A is equal to the integral over A of df star n dm dn. Right? So it's the function that tells you how this measure is distributed in your space. So what does it look like?
0 out of 1 0 2
Exactly, right? So, in fact, I should have drawn this a little bit different. Let me draw this a little bit differently because we're going to need much more space. So let me say, let's suppose this is the interval 0, 1, okay, and this here. This is 1, well, I'm not going to be able to, okay, so this is 1/2, okay, so the density is a function that has value 2 here and 0 here, right, so this is equal to 2 for x between 0 and 1/2 and 0 for x in 1/2, 1. This is what the density looks like. Okay. Now, what about the density of f star 2 n? What about the measure f2 star n? What does it look like? So this is is equal to m of f minus 2 of a. That's right. So if the only points that have second pre-images are the points between 0 and 1/4, right? Because this map here sends the f of x equals half x maps 0.1 to 0.1/2, and it maps 0, and then the next iterate of the map maps this to 1/4, right? So here we have 1/4. So the map, in some sense, you can write this map as 1/4. Right? So f2 of x is equal to 1/4 of x. You can write it very explicitly like that, right? And therefore, the only intervals that have pre-image are the intervals between 0 and 1/4. Okay? And for these intervals, the size of the pre-image will be 4 times as big. Right? So in this case, we have f minus 1 of a, and we have that the Lebesgue measure of minus 2, f minus 2 of a is equal to 4 times the Lebesgue measure of a. If a is in 0, 1/4. Okay? And if a is in 1/4, 1, then the Lebesgue measure of f minus 2 of a is equal to 0, because f minus 2 of a is empty. It does not have any pre-images by this map. So what does the density look like for the f2? So this is this was the density of f star m of a. Now we take f2a. So what is this density now here?
It's concentrating.
It's concentrating here, right? So it's concentrated in 1/4, and it goes all the way to 4 here, right? So it's like this. So now this density is equal to, when you take 2, it's equal to 4 for x in 0, 1/4, and 0 between 1/4 and 1. This is the density of f2 star. Okay, so we can easily see what is happening as we go on. What is happening, you will just get this concentrated more and more and more. Okay, and so what measure is this? I mean, in this particular case, the fact that you're taking the averages is not really very relevant. Okay, you're basically taking averages, but these measures here are getting more and more concentrated in very, very tiny neighborhoods of 0. Right? When I is 100, you are in 1 over 2 to the 100, right, interval, and you have a huge density. Okay, it's still a probability measure, but that probability measure is completely concentrated in this very, very small neighborhood. So when you take the averages, you will also see something that is slowly, when you take the averages, not completely concentrating, because you're still taking, a little bit of contribution from I equals 0, 1, 2, and 3, but as n becomes bigger, it's still, the average is still concentrating here. And what is the limit of this sequence mu n? Is the Dirac delta in 0. Okay, you can easily check that. Let me leave that as a simple exercise to check. Okay, exercise. In this case, we have that mu n is converging to the Dirac delta in 0. Which is not absolutely continuous with respect to the vector. But it is invariant. Okay, so this is consistent with a general feeling that, well, not general feeling, the fact that we prove that in general any accumulation point, any limit point of this is invariant, okay? But what we would like to show is that for our class of maps, this limit is absolutely continuous, okay? And the thing about this exercise, it also gives you a bit of an intuition of how what you should control to get the absolute continuity, right? What is the problem here is if the region in which the measure lives is becoming singular, then the density must blow up because it is still a probability measure, right? The average, it still satisfies this property, it's still a probability measure, so the density, the value of the density multiplied by the Lebesgue measure of the region in which this density holds always has to be equal to 1. So if these measures are supported in smaller and smaller region, the density must be blown up. So heuristically, you can argue that perhaps if you can stop the density from blowing up, then you're forcing the measure in some sense to not concentrate on some region. Okay? And that's exactly what we're going to do in our case. So we're going to show the key technical step is the following. So for each of these we can so we have that each of these is absolutely continuous, as we can show here, and we let Hn be the Lagrange-Nikodym derivative of each of these, okay? And then we're going to show this fundamental proposition that says that if f, okay, again in our setting of theorem, so f I to I, C2, full branch, satisfying 1 and 2, okay, those two conditions, so these are the assumptions of the theorem. Then there exists k greater than 0 such that two properties, so one such that the value of this, so the infimum over all nx of this is bounded away from 0. So this density is bounded away from 0. It is also bounded away from infinity. So the sup over all n and over all x, h and x, is bounded away from infinity. And for all n greater than or equal to 1 and all xy in the interval, we have that h n of x minus h n of y is less than or equal to k h n of x times x minus y So this is saying that this density is Lipschitz continuous, okay, with a Lipschitz constant that is independent of n and depending on hn of x, but we've just shown that also hn of x is bounded above by something that is uniformly bounded above. So here I wanted to put k here, yes. So there exists a k such that this is bounded away from k, which in particular is bounded away from infinity. So this is uniformly bounded, so this is actually less than or equal to k squared x minus y. So you can see clearly that these properties do not hold in the example, in the counterexample we just did before, right? I mean, besides the fact that this is not bounded away from 0 because we have these legions of 0, it is not uniformly also bounded above from K, it's not Lipschitz continuous. So these will really be properties that come from the full branch property and conditions 1 and 2 that we assume in the theorem. So in the last 10 minutes, what I want to do is prove the theorem assuming this. This fairly easily implies our theorem, and then in the next lecture we will prove this proposition, which is the core technical part of the proof. So proof of theorem assuming proposition. Assuming position. Okay, so what does this proposition says? It says that we have a family of Lipschitz continuous maps. Okay, so by proposition Hn is a family of equi-Lipschitz, all with the same Lipschitz constant, all uniformly bounded above and below. Okay, so what do we know when we have a family of equi-Lipschitz, in particular continuous equi-Lipschitz, okay, uniformly bounded, So as soon as you have that, you know you need to apply which theorem? Ascoli-Arzelà theorem that says what? Exactly, that there's a converging subsequence, okay, that converges to another function which also satisfies the same Lipschitz bounds as this. The same bounds and Lipschitz bound, okay, so now this converging, this limit point does not need to belong with this family, right? All it says is that you remain within the space of these uniformly bounded and uniformly Lipschitz functions. So by Ascoli-Arzelà, there exists subsequence H and J, okay, converging to some H satisfying the same bounds. Same bounds. Okay. As this. So H is a Lipschitz function on the interval bounded above and below. Okay, so it's a very nice function. H is going to be, so here we have our interval 0, 1. Okay, H is a very nice Lipschitz, not necessarily differentiable, okay, but it's bounded above and below, and its Lipschitz is very nice. And now we can use this to define a measure. Let's define the measure that has H as its density, right? So let mu equals, so mu define, let mu be a probability measure satisfying mu of A equals integral A H dn. So now this measure is, by assumption, absolutely continuous with respect to the Lebesgue measure. Okay? We just need to show that it's invariant. We claim that this is the measure we're looking for. Okay? So in some sense we've gone a little bit by a different path, right? So here what I said is that when we define the sequence of measures, we showed that that every limit point of the sequence of measures is automatically invariant. Okay? But now we've gone to choose our limit point, we've gone through a slightly different path in the sense that we are taking advantage of the fact that these are absolutely continuous, so we're passing to the densities, and we have a non-trivial statement about the uniform Lipschitz bounds on the densities, and we use this to construct a new density, okay? And this does not, essentially does, but it's not an immediate fact that this new measure is actually a limit point of this, okay? So we cannot just automatically apply the fact that this is invariant because it's a limit point of this, although essentially it is. We just need a couple of steps. In fact, we will show a slightly even stronger property of this to show that it's invariant. So, so mu is absolutely continuous with respect to Lebesgue. So just need to show that mu is invariant. And there are two simple steps which I will maybe sketch here. In fact, the first step shows a little bit even a stronger form of convergence of the corresponding sequence. So of course here, this sequence here corresponds to some mu nj, so there is a sequence associated to this. But what we have is that if we take a mu a, then we have this by definition is equal to h dm, okay? And this is by definition of h is equal to a limit of h and j dm, right? Because h is this limit of this subsequence, okay? And then we use the dominated convergence theorem to show that this is actually equal. We can take the limit outside the integral, and we get limit of h and j dm, right? And this is actually equal to the limit of j tends to infinity. Now, this is the density by definition of mu and j, right? So this is the density. This is exactly mu nj a. Okay, so we're showing that actually when you construct the measure in this way, you get that for every set, the measure of the set is the limit of these, and this, what we want is to write this actually according to the definition. This is equal to the limit as j tend to infinity of 1 over n, the product of fi star and a, right? For this is nj, I equals 0 to nj minus 1, okay? And this is equal to the limit as j tends to infinity of 1 over nj, sum of n by definition f minus I of a, right? I equals 0 to n minus 1. Okay, that's just one line, and then this next line so using this, we then just get that mu, okay, let's see, so mu of f minus 1 of a is equal therefore to the limit of as nj tends to infinity. So I'm going to use this, okay, is equal to the limit of the sum I0 to nj minus 1 of the measure of f minus I of f minus 1 of a. Okay, so I'm using exactly this property here in this first line with f minus 1 of a instead of a. And then this is just the usual kind of, manipulation, and you move things around, so maybe I'm not. So this is just equal to the limit of nj goes to infinity of 1 over nj, the sum of I equals 1 to nj of the measure of f minus I of a. Okay, so I've just absorbed this f minus 1 into the limits here, and then you do the usual stuff that we did exactly like in the other case. So limit of nj tends to infinity of 1 over so how did I write it down? 1 over nj times the sum of I equals 0 to nj minus 1 of the measure of f minus I of a, and then plus or minus 1 over nj f minus nj of a minus 1 over nj measure of a. Okay, now this is exactly, we just checked, this is exactly the same as we did when we were looking at the limit of the measures, and these measures, these limits go to 0, right? So this is just equal to the limit as nj tends to infinity of 1 over nj, the sum I equals 0 to nj minus 1 of measure of f minus I of a, which is just exactly equal to the definition of mu of a using that again. Okay, so this is just a few standard steps which are not completely trivial to follow, but which you can easily just carefully think about. Okay, so mu is f invariant. It's absolutely continuous and therefore ergodic. Okay, and it's invariant. The Lipschitz continuous is bounded, the density is bounded above and below, so we have a lot of information.
But why is it unique?
Ah, good question. I did not prove uniqueness yet. Okay, I will give a formal proof, but tell me why you think, what do you think? Why should it, could you have two measures with these properties? Can you have two measures that are invariant, ergodic, and supported on the whole interval? Because this is one subtle but key point that derives from the fact that this function is bounded away from 0, means that the measures are bounded on the whole interval, are supported on the whole interval. So can you think why, if you have two such measures, why you cannot have two distinct such measures? It's a good question. It's not just, it does not depend, you need to use the fact that they're invariant and the dynamics. Of course, you can have, on the interval, there's infinitely many absolutely continuous measures, right? For any choice of density, you have a measure that's absolute, but both of them are invariant. And the invariance has a dynamical consequence. What's the dynamical consequence of invariant? Of ergodicity and invariance? Yes, but we really have to use Birkhoff's ergodic theorem. So what does Birkhoff's ergodic theorem say for ergodic, it tells you something about the dynamics. It tells you that the measure is describing the dynamics of almost every point. Right? It says that if you look at the asymptotic frequency in any regions of phase space, it will converge to the measure of that region. Right? So if you have one of such measures, then it's saying Lebesgue almost every point has a certain frequency of visits to all the regions which are described exactly by that measure. Right? Now if you have another measure, you say the same thing. You say, okay, by this other measure you also apply Birkhoff's ergodic theorem, and Lebesgue almost every point has frequency of visits to a region that is described by this other measure. But then the measures of every set of positive measure has to coincide, because the dynamics itself does not depend on the measure. The dynamics itself, the frequency of visit to a point is just a frequency to a region, it's just a frequency of visit to a region. I will write out formally the proof next time. Okay? Please remind me if I forget, because you're right, this is an important point, is the uniqueness, is a simple argument using Birkhoff's ergodic theorem. You can try to think about it, but I will give it next time. So we're not completely proved. We're not completely finished. You just need to show uniqueness.